Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In this lecture video, I will discuss about polarization. So let's get started. The content of this lecture video is as follows. First of all, I will discuss about the introduction to polarization of light. Followed by, I will discuss following points: unpolarized light, plane polarized light, Tourmaline quartz crystal, plane of vibration, plane of polarization, and Brewster's angle. What is polarization? Polarization in physics is defined as a phenomena caused due to the wave nature of electromagnetic radiation. Sunlight travels through the vacuum to reach the earth, which is an example of electromagnetic wave. These waves are called electromagnetic waves because they form when an electric field that interacts with a magnetic field. The French scientist Arago noted that light reflecting off glass at an angle had special properties. Further experiments convinced him that these properties came about because light is a transverse wave. He named these properties polarization. Let's discuss polarization phenomena by picket fence analogy. In figure, waves set up in a rope passing between the slats of the picket fence can vibrate only in a plane parallel to the slats. If the rope passes through two picket sections with slats at right angles, now waves in the rope can pass through both. If you imagine a third fence with slats at 45 degrees, you would have predicted the wrong result. This simple experiment has shown how this much used analogy is imperfect. Hence, we need to understand the nature of light as an electromagnetic waves, which we have already discussed in previous lecture videos. Now try to understand the polarization phenomena in detail. Light is an electromagnetic wave and the electric field of the wave oscillates perpendicularly to the direction of propagation. Light is called unpolarized if the direction of this electric field fluctuates randomly in time. Many common light sources such as sunlight, halogen light, LED spotlights, and other bulbs produce unpolarized light. If the direction of the electric field of light is well defined, it is called polarized light. The most common source of polarized light is a laser. We will discuss laser and its mechanism in detail in next unit. Depending on how the electric field is oriented, we classify polarized light into three types of polarization. First is linear polarization. The electric field of light is confined to a single plane along the direction of propagation, which is shown in this figure. This figure shows that the electric field of linearly polarized light is confined to the YZ plane, which is shown in the left, and the XZ plane, which is shown in right hand side, along the direction of propagation. So this is called as a linear polarization. Next type of polarization is circular polarization. Circular polarization is the electric field of light consists of two linear components that are perpendicular to each other, equal in amplitude, but have a phase difference of pi by 2. The resulting electric field rotates in a circle around the direction of propagation, and depending on the rotation direction is called left or right hand circularly polarized light, which is shown in this figure. This figure shows that the electric field of circularly polarized light, which is shown in left side, consists of two perpendicular equal in amplitude linear components that have no phase difference. The resultant electric field wave propagates along the YX plane. The electric field of circularly polarized light, which is shown in the right hand side figure, consists of two perpendicular equal in amplitude linear components that have a phase difference of pi by 2 or 90 degree, The resultant electric field wave propagates circularly. So this is called as a circular polarization. Third type of polarization is elliptical polarization. In elliptical polarization, the electric field of light describes an ellipse. This results from the combination of two linear components with differing amplitudes and or a phase difference that is not pi by 2. This is the most general description of polarized light, and circular and linear polarized light can be viewed as a special cases of elliptically polarized light as shown in this figure. In this figure, the circular electric field, which is shown in the left hand side, has two components which are of equal amplitude and have a pi by 2 or 90-degree phase difference. If the two components, however, have differing amplitudes, or if there is a phase difference other than pi by 2, then they will create elliptically polarized light, which is shown in right hand side figure. This is called as a elliptical polarization. Now let's see what is unpolarized light. Unpolarized light, a light wave that is vibrating in more than one plane, is referred to as unpolarized light. A light wave is an electromagnetic wave that travels through the vacuum of outer space. Sunlight and almost every other form of natural and artificial illumination produces light waves whose electric field vectors vibrate in all planes that are perpendicular with respect to the direction of propagation. Such light is called as a unpolarized light. Diagrammatical representation of electromagnetic waves is shown in this diagram, which shows the direction of electric and magnetic fields which are mutually perpendicular to each other. This diagram we have already discussed previously. The symbolic representation of unpolarized light is shown here. Now let's see what is polarized light. If the electric field vectors are restricted to a single plane by filtration of the beam with specialized materials, then the light is referred to as plane or linearly polarized with respect to the direction of propagation. And all waves vibrating in a single plane are termed plane parallel or plane polarized light. The human eye lacks the ability to distinguish between randomly oriented and polarized light, and plane polarized light can only be detected through an intensity or color effect, for example, by reduced glare when wearing polarized sunglasses. In effect, humans cannot differentiate between the high contrast real images observed in a polarized light microscope and identical images of the same specimens captured digitally or on a film and then projected onto a screen with light that is not polarized. In this diagram, you can see that unpolarized light, that is only electric vector, when passes through a polarization filter, which is vertically transmission, then finally on the screen we get linearly polarized light. Now let's see what is plane polarized light. The basic concept of polarized light is illustrated in this animated figure for a non-polarized beam of light incident on a linear polarizer. Electric field vectors are depicted in the incident light beam as sinusoidal waves vibrating in all directions. In reality, the incident light electric field vectors are vibrating perpendicular to the direction of propagation with an equal distribution in all planes before encountering the polarizer. The polarizer illustrated in this figure is actually a filter containing long chain polymer molecules that are oriented in a single direction. Only the incident light that is vibrating in the same plane as the oriented polymer molecules is observed, while light vibrating at right angles to the polymer plane is passed through the polarizer filter. The polarizing direction of the polarizer is oriented vertically to the incident beam, so it will pass only the waves having vertical electric field vectors. Such light is called as a plane polarized light. The basic concept of partially plane polarized light due to refraction and reflection is illustrated in this figure for a non-polarized beam of light incident on a polarizers. The unpolarized light gets partially polarized due to refraction of light when it incident on a surface like quartz, whereas it also gets reflected from the same surface which is completely plain polarized light. This concept can be used in some applications where completely polarized and partially polarized light is used. Here are the basic symbols which are used to represent the light. In figure A, electrical field vectors of unpolarized light is shown. In figure B, vertically plane polarized light is shown. In figure C, horizontally plane polarized light is shown. Whereas in figure D, unpolarized light is shown. So these symbols are mostly used to represent the type of polarization as well as the type of light. The first clues to the existence of polarized light surfaced around 1669 when Bartholin discovered that crystals of the mineral Iceland spar, which is a transparent colorless variety of calcite, produce a double image when objects are viewed through the crystals in transmitted light. During his experiments, Bartholin also observed a quite unusual phenomenon. When the calcite crystals are rotated about a particular axis, one of the images moved in a circle around the other, providing strong evidence that the crystals are somehow splitting the light into two different beams. The schematic shows in this figure in which unpolarized light electric field oscillates in all directions, which transmits through polarizer, object which causes polarization, in this case a natural crystal of CaCO3, and finally gets plane polarized light for which electric field oscillates in only one direction. Now let's discuss about tourmaline quartz crystal. Tourmaline is a crystalline boron silicate material compounded with elements such as aluminum, iron, magnesium, sodium, lithium, or potassium. Tourmaline is classified as a semi-precious stone. This gemstone can be found in a wide variety of colors. The most common species and varieties that are associated with the term gemstone are diamond, sapphire, ruby, emerald, and tourmaline as shown in this figure. Tourmaline is a ring silicate with a silicon-oxygen ratio 1:3. In this diagram, in hand sample, columnar crystals with rounded triangular cross sections can be seen with concentric color zoning may be observed in end sections. Deep color may mask interference colors. In plane polarized light, tourmaline crystal experiences maximum absorption perpendicular to polarizer, that is the C-axis, which is shown in this diagram. This means that they appear darkest when the long grain is oriented perpendicular to the polarizer. The polarizer or analyzer can be made by having a slice of such crystals as shown in blue shade in this diagram. The concept of polarizer and analyzer we will discuss in detail in next lecture videos. Now let's discuss about plane of vibration and plane of polarization. When ordinary light passes through a tourmaline crystal, only those vibrations that are parallel to the crystallographic axis AB pass through, as shown in this diagram. Thus, the emergent light has its vibrations confined to a single plane only. Now we will define certain relevant terms. So that terms first is plane of vibration. The plane containing the optic axis in which the vibrations occur is known as the plane of vibration. The plane of vibration of a polarized light wave is generally unchanged in passing through a transparent material. It remains polarized in a similar plane. In the figure, ABCD represents the plane of vibration. Second term is plane of polarization. The plane which is at right angles to the plane of vibration and which contains the direction of propagation of the polarized light is known as the plane of polarization. It is the plane in which the magnetic vibration element of plane polarized electromagnetic radiation lies. The plane of polarization does not contain vibrations in it. In this figure, PQRS represents the plane of polarization. Now let's see how to detect plane polarized light. One cannot differentiate between unpolarized and plane polarized light with bare eyes. This can be done through the use of crystal that can act as a polarizer as well as an analyzer. Consider in this figure a tourmaline crystal or nickel prism used to obtain plane polarized light is called polarizer. Another such crystal to analyze and study the nature of light acts as the analyzer. Ordinary light on passing through the polarizer becomes plane polarized. If the analyzer is rotated in the path of transmitted light such that their axes are parallel, the intensity of light is maximum. However, the intensity becomes minimum when the axes of the two crystals are kept perpendicular to each other as shown in this diagram. Now let's discuss about Bristol's angle, which is represented by the notation theta subscript capital B. Bristol's angle, also known as polarization angle, is an angle of incidence at which light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflection. When unpolarized light is incident at this angle, the light that is reflected from the surface is therefore perfectly polarized. This special angle of incidence is named after the Scottish physicist Sir David Brewster. The principle behind Brewster's angle is illustrated in this figure. For a single ray of light reflecting from the flat surface of transparent medium having a higher refractive index than air, the incident ray is drawn with only two electric vector vibration planes but is intended to represent light having vibrations in all planes perpendicular to the direction of propagation. When the beam arrives on the surface at a critical angle, which is Brewster's angle represented by the variable theta in figure, the polarization degree of the reflection beam is 100%, with the orientation of the electric vectors lying perpendicular to the plane of incidence and parallel to the reflecting surface. The incidence plane is defined by the incident, refracted and reflected waves. The refracted ray is oriented at a 90-degree angle from a reflected ray and is only partially polarized. According to Brewster's law, when an unpolarized light of known wavelength is incident on a crystal surface, it experiences maximum plane polarization at the angle of incidence, whose tangent is the refractive index of the crystal for the wavelength. Further, the polarization angle is also called Brewster's angle. According to this law, when light is incident at polarizing angle at the interface of refracting medium, the refractive index of the medium is equal to the tangent of the polarizing angle. Therefore, mu is equal to tan of theta b. This is also defined as the angle between reflected light ray and refracted light ray is 90 degree, which is shown in previous figure. Therefore, according to Brewster's law, mu is equal to tan of I, where mu is a refractive index of the medium and I is the polarization angle. Therefore, according to Snell's law, mu is equal to sin I upon sin R. Let's say this is equation number 1. Therefore, according to Brewster's law, mu is equal to tan of I is equal to sin I upon cos I. Let's say this is equation number 2. Comparing both formulae which are in equation number 1 and 2, we can write cos I is equal to sin R is equal to cos of pi by 2 minus R. Therefore, I is equal to cos of pi by 2 minus R, or I plus R is equal to pi by 2. As I plus R is less than angle ABC, which is shown in the figure, is also equal to the pi by 2. Therefore, the reflected and refracted rays are at right angles to each other, that is 90 degree. One general example of the application of Brewster's law is polarized sunglasses. These sunglasses use the principle of Brewster's angle. The polarized sunglasses reduce glare, that is reflecting directly from the sun and also from the horizontal surfaces like road and water. Photographers also use the same law to reduce the reflection from reflective surfaces by using polarizing filters for the lenses. This is all about introduction to polarization of light and its type: unpolarized light, plane polarized light, the introduction upon Tourmaline quartz crystal, plane of vibration, plane of polarization, and Brewster's angle. In my next lecture video, I will discuss about Malus law, double refraction in calcite crystal. So please don't miss my next lecture video. Thank you. Video in the description. The link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.